seeing you here.
Yeah.
Okay. Okay. That kind of okay. All right. I think we're good. That's. It's week 4. Hooray! Week 4. Hello everyone. Welcome to Event-Driven Computing Week 4. This week we are looking at some ways of implementing FSAs. Well, particularly we're interested in FSAs that are we have to deal with output from them, as opposed to what we've been looking at so far, which are basic FSAs where they don't necessarily do much. Like, we use them to evaluate a sequence of inputs or something to that effect, but they don't actually have to do things once we run them. We just sort of run them and we take a look at what state they're in at any particular time, and that's the extent to which we use them. So that's what we've been looking at. Hopefully, again, you've all had a read of the notes for this week, so you should all be across this. We're going to work through one biggish example. We're going to look at the different ways that we can approach it, and we're also going to have a bit of a look at how we might implement that into some basic code structure. All right, programming assignment 1 is still available. Sorry for any confusion with the announcement. The submission portal will open for that on Friday. It's due at the end of week 6. There are no workshops this week. Workshops run every other week. It's odd weeks only, and the census date is on Wednesday. So if you are considering dropping this course, you should do so before Wednesday. Otherwise, you're stuck with me. Okay. As usual, feel free to ask any questions in the live Q&A in Piazza right now, or in the discussion in Echo 360, which I will be keeping an eye on throughout the session. And hello to the 3 of you currently watching live. I really got to get timetabling to schedule this later next time around. Anyway, that's life. They're not a fun time for anyone, myself included. Okay, so with that in mind, merely more machines. This covered more part of slide than I anticipated. Okay, all right, well, let's build. This is all of them. So the bit that's cut off at the bottom is we're going to take a look at this example as a merely machine, a more machine, and a merely more machine, and then we will consider how we might approach coding such an example. I'm going to switch away from the giant black texter this week and go to pen, because it's going to require a bit more precision in what we're drawing on the page than we've been doing so far. So we are designing a system, or designing software for a new automatic garage door opener. Some of you may recognize this example from week 1, and we said just how might we approach this as like a basic event-driven system. So now we're revisiting a slightly more complicated version of this system as an example for each of the merely and more and various things. And the reason why we're revisiting this particular system now as opposed to earlier is because we have outputs that we're interested in. So whereas previously we were just looking at evaluating the state of the system at any given time, now we have things that we want to actually do. We want to trigger the door to open or close and take actions depending on the various different inputs to the system that we are interested in. So let's just go through the text, we have a garage door. It has an electric motor that raises and lowers the doors. There is a switch or like a sensor that detects whenever the door hits something. If the door hits something when it's lowering or raising, that switch is going to trigger. Not sure why it would hit something when it's raising, but we're really only interested if it's going to crush someone. We want to avoid that happening. So we have a switch that will detect if the door bumps into anything. We have a sensor that indicates when the door is fully open. We have a sensor that indicates when the door is fully closed. And then we have a remote, and it's a single button remote. You press the button once, and if the door is closed, it's going to open. If the door is open, it's going to close. If it's halfway through opening, it's going to change direction. And same thing if it's halfway through closing. And we've also explicitly noted that when we first turn the system on, the door is going to close itself. So that's something to be aware of. And I think that's all of the key bits and pieces. Oh, if a door hits something while it is closing, it is going to open back up again. So that's that switch. So we want to try building this system as a Mealy machine. We're going to try building it as a Moore machine. And as a Mealy Moore machine, we're going to discuss the comparative differences between all three approaches, and then we're also going to look at the code implementation. Okay. Start with the basics. How are we doing? Way out of focus we are. Come on. Boop. Oh, it's struggling today. Okay, that's that. That's maybe a little bit more out. That's as far as we can go. Okay. All right, so the way that I like to approach this type of a question, just to start off with, is I want to identify all of the inputs and outputs that the system has connected to it. So what are the outputs that we have noted, or the things that we can, the actions that we can take out of this system?
Oh, that wasn't rhetorical.
That wasn't rhetorical, no. That said, if the chat is going to answer, we could probably give them a couple moments, but again, I think there's only 4 of them in there, so whenever.
The door closes, door opens.
Yep.
The door hits someone or something.
Yeah, those are possible event triggers, but what are the actual outputs that the system can provide? So the door opening and the door closing, the door hitting something are all events within the system. Event-driven computing, yay! But what are the outputs from this system that we've just described? Again, feel free to post in the Echo 360 live discussion or in Piazza.
So is that only one accepting state? So that's why just if the state at the accepting state, so the system will tell you that all the process is finished.
I would potentially argue that in a system like this, do we have an accepting state? Like, is the system ever going to be defined as finished for a garage door that you can open and close and open and close? And
I assume that every system should have one accepting state. Is that right?
not necessarily, no. Systems don't need to have an accepting state. It's, sorry?
Theoretically, it could be when the door is closed, but then the door can just be reopened again, so it doesn't really necessarily apply.
Yeah, theoretically we could say that when the door is closed, the system is in an accepting state. We might want to use that, for example, if we wanted to have some sort of safety lock in place to make sure that the door is shut when we turn the system off, if the system gets turned off. Or alternately, if the system is going to get turned off, that the door fails into an open state or something like that. Then we might want to apply an accepting state in that way. But In terms of like a practical system where we're trying to deal with having to take actions and a system that potentially can run forever and that we're perfectly willing to have run forever because ideally we start this thing going and it just works forever, I would say that an accepting state isn't actually required in this type of system. So we're moving a little bit away from the basic FSA definition that we've been working with so far, where we actually deal with accepting states. We can still have them, but they're less common in this type of a system.
Would the direction it moves in be the outputs?
Potentially, yeah, to some extent. It's a bit of an ambiguous question if we're not quite in the headspace yet, or if like I'm talking on a different wavelength than you all. So for our purposes, the outputs of this system, let's go ahead and, oh, there we go. I'm just going to put a little mark in, where's the bottom, where's the bottom, where's the bottom? There. Okay, so the outputs from this system, which refers to, in this case, it's the actions that the system is capable of taking as a result of some set of inputs. So in this case, our outputs are close the door and open the door, or at least that's going to be run motor, and then I guess we can decide whether forwards or backwards is closing or opening. Let's say forwards is closed, and this might be run motor backwards. All right, so let's say for argument's sake that forwards is closing, backwards is opening. Depends on your system and your motor. Maybe you've wired your motor the other way around, in which case backwards could be closing and forwards could be opening. That is an entirely arbitrary decision for the system that we're trying to develop, but the idea is our outputs are the actions that we can take based on the inputs that this system receives are closing the door and opening the door. Maybe we have a system with like a display output, in which case, you know, maybe we want to display a certain number on the display, or maybe we want to like flash a light or beep a buzzer or something like that. Those of you who have done digital electronics, this will seem a little bit familiar, albeit probably you've done digital electronics maybe 3 years ago, so this might seem a bit familiar, but a bit of a refresher here, and we're also looking at some slightly different bits and pieces, or some slight variations on what you might have done there. So those are our outputs. What are our inputs into the system? Hopefully this one should make a bit more sense.
The button presses
Yep, which button?
on the remote control.
Yep.
Yeah,
Okay, yeah, I'm just going to call it remote button.
there's only one.
And what else have we got?
The initial state where it automatically closes the door.
Is that an input into the system? No. That's where we want to start the system, but yeah, that's not an input per se. Although, I mean, one could argue that because we started, like, yes, we're taking an action based on the fact that the system is starting up, but that isn't necessarily an input into the system per se, in the sense that we consider all of the other things inputs into the system.
The sensor.
Yep, so we have, I'm going to say sensor top, or open maybe. Let's just call that open. Okay, so we have the button on the remote, we have the two sensors, one for when the door is open, one for when the door is closed, and last but not least,
The bumper switch?
Yeah, the don't get crushed switch. Okay, so these are our 4 events in the system. So the button on the remote being pressed would trigger an event. The sensor when the door is fully open, that's going to trigger an event. The sensor when the door is fully closed. Now we could sort of discuss back and forth about whether the sensor for when the door is opened is constantly triggering once the door is open, or whether it's just a one-off trigger. We'll say for argument's sake that it is a one-off trigger when the door reaches a point where it's open. That's going to trigger the sensor. That's just going to trigger once. Although arguably we should be accounting for what happens if the sensor is constantly triggering anyway. We have the one for closed, and then we have the sensor or switch on the bottom of the door that is going to detect if the door hits something. Right, so those are our inputs, these are our outputs. Let's go ahead and build out this system. Now there were 3 different approaches that we've looked at. There was the Mealy approach, the Moore approach, and the Mealy-Moore approach, and we will just start off with a basic Mealy machine. If you've done digital electronics, then you might have done a Moore machine to start off with. We'll look at both and talk about why you might do one over the other. So in a Mealy machine, we associate the actions that we want to take with what?
The inputs and the present state.
Yes, but in terms of actually taking the action, what do we associate taking the action with? Again, feel free to post in the live discussion or in Piazza, for those of you watching live.
The transitions.
Yep, exactly. Yeah, in a Mealy machine we associate. Oh gosh, the volume. In a Mealy machine we associate the actions that we take with the transitions themselves. So as we leave a state, we can then take some actions depending on the input that we've received, then we arrive in another state. So the states themselves don't have any inherent actions associated with them. So because all the actions are associated with the transition, let's just start by initializing the system. So the actual entry into the initial state, the transition into the initial state as we start the system, that's going to trigger our initial actions, probably. So we use circles in a Mealy machine, but I'm not going to be too fussed if you switch between circles and squares in different ones, or if you get them mixed up in an assessment. So lightning bolt as usual to indicate the state that we're entering into, and then we are going to add behavior. Wrong one. Okay, that one, okay. The motor operates to lower the door until it is fully closed. All right. Yep, so. Wow, that would have caused some problems. Oof.
What's up?
This was a past exam question, and there is some room for confusion in here.
From which year?
2018, I think. This was in 2018, maybe. Okay, so the motor operates to lower the door until it is fully closed. So we actually need an entire initial set of states to handle the fact that the system could potentially be in an open state.
Could we simplify it to just pass through the function closed or when the initial
We-
state occurs?
I imagine that is what the I imagine that what is what this exercise is aiming for, that we actually want to close the run motor forwards function when the system initializes. So,
And
or we could argue that the system just initializes straight into the closed state and skip all of that, and maybe we come back to this later and say, okay, well, how would we actually handle the fact that the system can initialize into any point, and we want to make sure that it then runs to ensure that it's actually in the closed state.
do you know if the exam asked whether you made any assumptions?
Well, as you know, you should always state your assumptions in an exam situation. So if you do make any assumptions, by all means state them in an exam. I'm going to assume that the but the question says it. Okay. No, the question definitely says it.
Maybe that part of the question got cut off.
Oh no, this up here is the whole question. That's
Oh.
yeah. This was just the we're going to do a Mealy machine. We're going to do a Moore machine and a Mealy Moore machine part. Okay. When the controller is first connected to power, the motor operates to lower the door until it is fully closed. We probably also have a motor stop event, don't we? Or a motor stop output. I'm going to add that in here.
Yeah, because that
Yeah.
would also apply for the bumper switch.
Yeah. Okay, so as part of this entry, we are going to run the motor forwards to close the door.
So now here we have four entry.
Mhm.
The first is the transmission entry is the.
Oh,
orange-
sorry, you guys can't see. Oh, this is going to get fun. All right. There we go. Okay. So I've
the-
added a stop motor and
So the entry is the remove button. When I pass the remove button, it's the first entry, right? And then the other entry is the bumper switch. Just two entries. Just two.
we have 4 inputs total.
Four inputs.
Yeah, so we
But the
have
center-
the remote button.
Passive. This is the sensor is passive, right? So passive is they get the environment
Mm.
information, and then they automatically to respond something.
Yeah, in an event-driven system, I mean, I suppose it depends on the sensors that you're working with in practice, but
Yeah.
in as this is event-driven computing and we're looking at event-driven systems, we consider these sensors to be active, as in something that when it is triggered, it will send an input to the system to say, I have been triggered, as as an input. So that's fine. In the same way that, I mean, one could argue that like a button is a sensor that is triggered when you press it, right? So in the same way, we could say that, okay, well, and we haven't actually, it hasn't really stated what these sensors actually consist of. Like the sensor could be a physical button that is triggered when the door closes. It might be, and like for example, in like an elevator system, this is something that does actually exist. They have physical switches at the top of the rails. When the elevator like reaches near the top, it will trigger an actual switch that will send an input to the system to say, hey, you're getting close to the top, you should slow down. And then there's like 2 more switches, and if you hit the 3rd switch, it's just like everything's broken, stop the elevator, and you get stuck in an elevator. Anyway, that's a fun little aside about elevators. But okay, so we initialize the system and we start by running the motor forwards, and we're going to do that until I think we can safely assume that the sensor is going to trigger if the motor is running forwards and the door reaches the closed position. So we're just going to start by adding that little bit in at the start. So what I like to do is I like to start with an initial state and just build the system out. Like with our DFAs, we want to account for every possible input at all points in time. And that means for every single state. So we will address each of these inputs as we build this system out. So we initialize by starting the motor, and then when we should have picked a better pen. So we run the motor forwards when the, why are these functions? I don't know why these are functions. When the sensor closed is triggered, then we stop the motor. We just write this out like pseudocode. I mean, you can use your preferred programming language style if you want. This is sort of standard pseudocode style. Looks a bit like Python, but essentially you have the event that is triggering something to occur, the thing that you do as part of that. So when the sensor closed is hit, we stop the motor, and that arrives us in this state here. Let's take a look at the other inputs that we have. So if the remote button is pressed at this point, do we want anything to happen while the system is initializing? This hasn't been defined in the problem description. I'm just going to say that maybe like when the system is turning on for the first time, it's going to close and like that's it. But we probably, for example, want to open the door if the bumper switch is hit. So I'm going to say that sensor open is probably going to do nothing. Although,
So was that first state basically like a transition state?
for this scenario, effectively, yeah. For another scenario where the system initializes into a sort of a ready state, this system doesn't quite initialize into a ready state. It initializes and then goes, oh, I need to do a bunch of stuff to actually put myself in a state of readiness. So, but not all systems are going to need that. Sensor open, and I do not leave myself enough space here. Remote button or sensor. So remote button or sensor open is just going to loop us and keep us in this state. So as we've sort of seen with the FSAs that we've been building out so far, the basic idea is that you have this state machine structure where you move from state to state to state, and depending on what state you're in is going to depend on what, in this case, what state you're in, depending on what state you're in, will determine what behavior or action you take based on each input at any given time. So previously we've just looked at that in terms of, does the system end up in an accepting state or not? Now we're looking at it in terms of what actions am I going to take and how do I represent those actions? And this has the structure that we use for this, whether it's a Mealy machine or a Moore machine or a Mealy Moore machine, is going to have a direct impact on how that structure plays out in the code that we're implementing as well, for consistency. Okay, so if the bumper switch gets hit, we probably want to go to a different state here. And if the bumper switch gets hit, we're going to want to run the motor backwards. I'm just going to shorten that to run backwards, or run back. Getting a bit messy. Okay, so if the bumper switch gets hit, we're going to run the motor backwards in order to open the door. And arguably this here is going to be then effectively the state for the door is closed, we're ready. And this one is the door is open and we're ready. Or maybe it's an error state, depending, but either way, well, no, actually, no, this is what am I talking about? This is the door is currently opening state. So, yeah, okay, so I'm just going to call this opening. Potentially, we could say that this is the door is closing state, and if we wanted at that point, we could actually go ahead and change this around and put the remote switch over here, because the problem description said that if you press the remote button while the door is closing, it's going to start opening. So to simplify things, we might actually do that. So, right, button. So, yeah.
Excuse me, I have a question. If in the initial status the store is already closed, why that status is not closing? So this closed.
So
This is.
yeah.
This is
So
closed.
I mean, we were talking just before about, okay, well, how do we interpret the initial state part? And one could potentially argue that the initial state, based on the question, the system should initialize into the closed state. But because the question text says that when the controller is first connected to power, the motor operates to lower the door. Oh, yeah, I suppose that could be initialized into the closed state.
Yeah, it's
But then how do we determine that it's closed? Ah. Gosh dang it. Okay.
Were you teaching this course when this exam was written?
I wasn't coordinating it, but I was, I think, tutoring the course when this exam was written. Yeah. Okay. Let's work on that assumption then. It is a reasonable assumption to make because it's one that I would expect students to make in an actual exam. So let's reset that. Start again. We will run. Oh gosh, can't write M's today. We will argue, for argument's sake, that that's just initializing into the door being closed state. Okay, so we have a door being closed state. When the door is closed, let's again look at all of our 4 possible events that could occur. We have the button being pressed, in which case, what do we want to have happen?
Opening.
Yep.
So we're initializing
So
it
I might-
into a ready state now.
Yeah, let's say we're initializing it into the closed state. In fact, I'm just going to run motor forwards and then stop motor, even though that's probably, again, we probably need like a full set of states to initialize the system in, like start by running the motor forwards and then waiting until we hit the stop, and then once we hit the stop, then we're in our initial state. And then if not, we keep going forwards, but then we also need to take into account the behavior of the bumper buttons. So potentially it makes more sense to do what we were doing before and initialize into the door is being closed state and sort of see what happens. But let's say that we initialize into the closed state. Again, state your assumptions if you're doing this in an exam situation. Okay, so assuming that we start here, so we run motor backwards to open, and that's going to put us into a state which we're going to call opening. So we have an opening state if the button is pressed. What do we do if we get, what about the other 3 inputs that we receive?
Bumper 3.
Yep. when the door is
Close.
closed and the bumper switch is triggered.
Uh, the trigger is sensor code because when you trigger the sensor code send the message to the system. It's still at the same stage, right?
Yeah, exactly. The door is already closed.
Yeah.
So if we are receiving inputs from the door is closed sensor or the door is open sensor, that's a little bit worrying if we're receiving triggers from the door is open sensor, but we probably don't want to do anything if we're receiving, if the door is stopped and stationary and closed and we receive an input from one of those sensors, we probably don't want to do anything. So loop back. And we can just do nothing for all of those. So this is bumper switch, and what do we call this? We call this sensor closed and sensor open, and our action is to do nothing. Okay. All right, we're on track now. Okay, let's take a look at this new state that we've just created. So again, the way that I like to build this out, it's nice if you can start by figuring out what all the states you're going to need are going to be. But that's not necessarily always the case, so I like to start with an initial state and just figure out what happens at each individual step and keep building out until we've exhausted all possible inputs at every possible state. So we've done all possible inputs in the closed state. Let's take a look at the opening state. So if I press the remote button when the door is opening, what do I want to have happen? Probably helps if I pull up these slides on another screen. No, we only have one screen in this room, don't we? Yes. The slides are on my uni if you want to pull the description up.
Theoretically, if I were using a garage door and it was opening and I pressed the button, I was expected to stop where it is.
Okay, yep. And what does the question say? Like, if the question didn't say, then absolutely state that that is your assumption and then roll with it.
Oh, it reverses direction.
Yeah. Question says it reverses direction, so we're going to put ourselves into a state where the door is closing.
Didn't realize it actually said.
Okay, and so this is going to be remote button. So if we press the button, that puts us into a closing state. We're going to take the action of running the motor forward. I can't write M's today. Okay, so we're going to run the motor forward. That is the action that we are going to take. I'm going to add.
A little bit worried that some people may not be able to read your handwriting.
That is a fair concern to have.
It's also very
I will try to make it a little nicer.
good.
Yeah. All right, so we're going to start running the motor forward, and that's going to put us into a state where the door is closing again. Okay, let's take a look at the other inputs at this point. If we are in the opening state where the motor is currently driving the door up or running backwards, and we receive an input from the, let's start with the bumper switch. What do we want to do?
If the system trigger the sensor open, and then the sensor open will send the instruction into the system, mention that the door is already opened.
Okay, yep, all right. So if we receive the, if the open sensor is triggered, then yeah, we want the system to recognize that the door is open, so it's going to have to stop the motor running at that point. So I'm going to call this open. And I'm going to say that that is...
The question only has a case for if the door hits an obstruction while closing, not one for if the door hits an obstruction while opening.
Yes, that is true. What do we assume should happen if the bumper switch is triggered while the door is opening?
Change direction and return to a closed position.
So, okay, so if the door is opening and the touch sensor that indicates the door has hit something has triggered while the door is opening, I suppose it depends on how the touch sensor is set up, arguably.
Because it says if the door hits an obstruction while closing, it changes direction and returns to the open position. So I would assume the opposite would be true while it's opening, that it changes direction and returns to the closed position.
Okay, so for everybody watching at home, the discussion that we're having right now is that what should we do when the door is currently opening up and the touch sensor on the bottom of the door that indicates the door has hit something is triggered. And so far the consensus that we have is that the door should stop what it's doing and reverse direction, because that's the behavior that we have when the door is closing and the switch that indicates the door has hit something has been triggered. I'm just going to throw this one out for a quick 2-minute poll just to see what everybody else is thinking about this one. Just to get, I'm going to throw that in Piazza. Let's see. What else?
I mean, similarly as before, I would expect the door to just stop where it is in a real world scenario.
Okay, so we have a couple of... Alright, so poll choices. What should the door do? Switch is hit. Poll choices, poll closes after 2 hours. Okay, that's fine. Poll selection, that's fine.
What was the other option that's going to be on the poll?
Oh wait, please select at least one folder. Okay, there we go. Okay, there we go. All right, so that poll is up in Piazza now. So I put 3 options in the poll. We've got the door should just stop where it is, the door should continue opening, and the door should reverse direction and start closing. And we'll just give that a couple minutes for people to have a think about. Feel free to add follow-up discussions and comments as to why you think it should be one or the other.
Sorry, where'd you put the... Oh, there we go. Found it.
Now, while we're deciding what should happen in that scenario, let's take a look at the rest of these and continue on. We'll come back to that particular case. So that was what should happen if the bumper switch is hit while the door is opening. What about if the closed sensor is triggered while the door is opening?
The system done a boo-boo.
What do we think that could mean if the door closed sensor is triggered while the door is opening?
Remain in the state.
From the opening state?
Yeah.
Yeah.
Just
Remain in the
should be no
state?
action.
Yeah. Yeah, I mean, I think there could be any number of reasons as to why the door closed sensor is triggered while the door is opening. Maybe the door closed sensor never stopped being triggered in the first place and it's repeatedly just being all like, I'm here and the door is still closed. Maybe, I don't know, maybe a kid kicked it or something like that, or depending on what type of sensor it is, someone walked through the door and that triggered it, whatever that could be. So yeah, I'm going to roll with remain in the same state, and we're just going to do nothing if the closed sensor is triggered. There we go. Alright, so that's what happened if the closed sensor is triggered. So we've got the remote button, we've got the open sensor, we've got the closed sensor. We're going to come back to the bumper switch depending on what people think in the poll. Let's move on to one of these other states. I'm going to move on to the closing state. What do we think should happen if the button is pressed, the remote button is pressed while we're in the closing state?
It reverses and starts opening again.
Reverses and starts opening again? Yep, that's exactly what the question says. So I needed to draw this diagram so much bigger. I should have used the texter. The texter makes me draw big. Okay, so if the button is pressed, we start the motor running back the other way. That's fairly straightforward. If we are in the closing state and the open door sensor is triggered, I think we can agree that that's the same behavior as if we're in the opening state and the closed sensor is triggered. So we're going to do nothing. And what did we say if the door bumper switch was triggered in the closed position?
You mean closing?
Closing, yep.
It
It reverses, yeah. So okay, so bumper switch or the remote button while the door is closing. Then we're going to change the direction of the motor and we're going to move back to the opening state. The door is now opening. And finally, if the door is closed sensor is triggered while the door is closing.
then move into a closed state.
Yep. Okay, so we're going to enact the stop motor behavior if that is triggered. So that is all 4 inputs there. Let's take a look at the open state. Okay, now if the door is open and the bumper switch is triggered, or either of the sensors are triggered, what should we do?
Leave it as it is.
Leave it as it is, same as if we're in the closed state. Okay, so any of those, and if we press the button, then we're going to start closing again, as you can imagine. think we said forward is closed. Okay. All right, we got there, and that's, well, we got there and we have reached a dead heat on what the door should do if we are, oh, wait. Wouldn't that depend on the configure? Oh, we have a question. Okay, so wouldn't that, so what to do with the bumper switch? And the question is, wouldn't that depend on the configuration of the bumper? For example, if the bumper is facing the closing direction, then triggering it wouldn't mean there's an obstruction. That is true. That does depend on the configuration of the bumper switch. Ooh.
What does that mean?
So going back to the deciding what the bumper switch should do if the door is opening and the bumper switch is triggered, and the question is, wouldn't that depend on the configuration of the bumper? So basically, if this was a touch sensor on the bottom of the door that gets triggered whenever the door hits something while it's closing, then they're saying, well, if that was triggered while the door was opening, that wouldn't mean that the door was obstructed necessarily, so that shouldn't necessarily result in that behavior. Again, lots of different questions that we should be asking about this, and it's going to depend on the exact mechanics and design of the system. I think if we had the actual garage door in front of us that we were designing, we would be able to make a much better we would be able to resolve those assumptions much more easily in terms of what should happen. I'm going to roll with that logic. I like that logic. So given that if the switch is something on the bottom of the door that triggers whenever the door hits something when it's closing, then if the door is opening and that button is triggered, then that shouldn't mean, then that's not a problem.
So it does nothing.
So I'm going to roll with does nothing for that.
Alright.
But I think that there are decent arguments in a variety of different directions for that. But that's our basic Mealy machine for this. So key characteristics of a Mealy machine are that all of the behavior is always associated with the transition that we're taking. So behavior is associated with the input. So a different type of system that we have is a Moore system, and this says, well, one of the things that we might notice about this system here is that whenever we transition either from opening or open to the closing state, for instance, the first thing that we're going to do is we're going to run the motor forward. So it's like, okay, well, because we always run the motor forward when we enter this closing state, then this seems like repeat behavior. We're constantly doing the same thing. It was like we have the same behavior every time we enter this state. Maybe instead of associating the behavior with the transition, we associate the behavior with the state itself. Yeah. It turns out that that associating the behavior with the state itself rather than the transition results in a more results in code that is very consistent with a basic FSA in terms of implementation, where if the behavior is associated with the state itself, then the code looks almost exactly the same as if you were implementing a basic FSA in code versus implementing a Mealy machine or a Moore machine. You'll find that the Moore machine looks almost exactly like a regular FSA. It's just that each state has this behavior tacked onto it. So what does that look like? We tend to draw the Moore machines with rectangles because we record the actions that get taken when you enter a particular state in the actual rectangle itself. So I'm going to start with the closed state again.
Looks like UML.
It does look like UML, yes. Those assumptions we made before are going to haunt me for the rest of today. Okay, let's see how we go. So whenever we enter the closed state, we want to make sure that the motor is stopped at that point. So I'm going to add the stop motor behavior. Now the whole initializing and starting off thing, that's just going to open an entire can of worms here that I'm going to come back to later at the end of the thing. If we have to trigger the door closing action as part of entering into the system, but the system initializes into the closed state, we cannot do that in a Moore machine. We would have to have a separate set of states to handle that. So
do we have to have a function that mentioned that the system is already ignited? So when the system is at the initial status, the system should be send a message to the all the motor mention that is the system is ready. Yeah. So that's maybe have a.
I mean, if that was a
initialized.
That doesn't work in this kind of architecture. So the question was, well, couldn't we transition states based on? I mean, that's what it boils down to. So what the question was, okay, well, when we initialize the system, couldn't we like have an initial state that we initialize into, and then that performs a bunch of actions, and when those actions are done, then we move to another state? And the issue with that is that that doesn't match the architecture that we're building. So obviously, like this kind of architecture does not work in all scenarios, but this is an architecture that is specifically designed to handle a system in which you have a series of different events and you need to take actions based on what event occurs at specific times. That's not to say that we couldn't have like a hybrid architecture that does go through a whole bunch of initialization stuff first, but completing the initializations in that sort of a system wouldn't normally trigger an event in the same way that all of the other inputs trigger events. So then we couldn't transition from that into another state. So we'd actually have to map it out as a separate state altogether in that instance. We'll come back to that. For the moment, we're just going to make an assumption that the system initializes and that the motor stops, and like that's that. So every time we enter the closed state, the motor is going to stop. We are explicitly going to issue the instruction to the motor to stop. So once we're in the closed state, I mean, we find that many of the transitions are going to look quite similar to our Mealy machine here. So let's start with the remote button. So when we press the button and we're in the closed state, we are going to start opening. So the system is going to transition to the opening state. And this is okay, and all the behavior is associated no longer with the transitions, so we do not have anything here other than the event that is triggering the thing that we're doing. And this is going to take us to the opening state. And when we enter the opening state, what do we want to do? We want to start the motor running to open the door. So run motor, I think we said backwards to open. And if we want to take other actions, we would put them on separate lines beneath each of these here. So starting closed, we press the remote button, moves us to this state here. We take these actions as we enter into the state. I'm going to come back to all of the other crazy things later on because this is going to get really messy very quickly. So we will do all the basic ones first. If we are in the opening state and the remote button is pressed, then the door reverses direction, same as what we said before. So we're going to have a closing state, and we're going to run the motor forward. Okay, that's the action that we're going to take. Anytime we enter this closing state, we're going to start the motor going forward to lower the door. So that's going to be a okay, so there's our remote button, and let's just keep going with this. We have the same thing back in the other direction. We can see that the transitions are really straightforward and tidy for this type of a system. It works really well for repetitive behavior that always occurs when you enter a particular state. So we press our button in either of these situations, we swap back and forth. As we enter each state, we are going to trigger this particular behavior. Okay, and then we're going to have our open state. And if we are opening and the open sensor is triggered, we don't even need that. That's just what happens when the open sensor is triggered. We're in the open state, and if we're closing and the closed sensor is triggered, and we end up in the closed state, and that's all fairly straightforward. And finally, remote button. Okay, now you might be wondering at this point, Ian, you just walked us through a Mealy machine. We handled every possible input at every possible state before we moved on to any of the other states, and I've been very explicitly avoiding that up until right now. Why is that? The reason for this is because the issue with a Moore machine is it's really good for code reuse in this sense. But one of the characteristics of a Moore machine is that anytime you transition in a state, you explicitly re-trigger all of the entry events of that state. So if I do a loop on, well, let's just start by doing a loop on closed. If I do a loop on closed like this, what this represents in the context of a strict Moore system is that I exit the closed state, and I re-enter the closed state, and I re-trigger all of these actions to occur. Depending on the system, I may not wish to re-trigger actions. Now, for the closed state, making sure the motor is stopped every time I receive any input into the system is probably not a problem, but I might not want to resend the signal to run the motor every single time when I'm in the opening state. Let's just roll with that. That's how we want things to work for the time being. So if we say we have the bumper switch, so if we're okay with the motor being explicitly triggered to stop every single time we enter the closed state, or even when we re-enter the closed state, but as you'll see in the example that's posted in my uni, there are actions that, some of the actions that we take, for example, incrementing a counter. We might not want to increment a counter every time we just stay in the particular state. It might be particular actions that we want to result in a counter being incremented, as opposed to some actions where just nothing happens.
A for loop as above loop.
Not quite.
Well, like, yes, so it's a for loop versus a while loop. We might not actually increment a counter, but in terms of if I was implementing counter functionality into an event-driven system where every time a particular event occurred, that would result in a counter being incremented if I was in a particular state. So just as we take a bit of a quick tangent. So if I have something like A++, this is an action that occurs, and let's say I have two inputs, A and B. Actually, no, let's go X and Y as two possible inputs. And let's say, if I have input Y here, for instance, I enter this state, and let's say once I'm in this state, whenever input X is occurring, I want to stay here and do nothing. Now, and if I was to represent that in a Mealy machine, I might represent that as something like this: Y A++. So I might represent it like this, where I'm incrementing this counter variable A, and then X, I just stay in the same state, but I do nothing. So I might have something like this. These two things are not the same, because this happens regardless of whether I'm coming in from Y or whether I'm looping on X. So this results in A being incremented every time X is triggered, whereas this only results in A being incremented whenever Y is triggered as we enter into the state for the first time. So the fact that we are remaining in the state in a Moore machine still triggers all of these events every single time. We might not want this to occur, in which case what we have to do in the Moore machine representation is we have to we don't want that. What we want to do instead then is we need to have a second state, which is like a dummy state. There's like a duplicate of this one. That does nothing, and let's say we had a third state down here that was triggered on like another Y, for instance. What we would then do in a Moore-based system is we would have the Y's from both of these converge, and then you can loop as many times as you want here with X, and it doesn't re-trigger this behavior to occur. So Moore is really good for like duplicate behavior that's always going to occur every time you enter a state, including if you are remaining in a state. But if you are have behavior that you do not want to have triggered every time you remain in the state because an event occurs and you explicitly leave the state and re-enter it, then you have to create all of these duplicate states and things start to get weird. So if we revisit what we were just looking at, if we didn't want to explicitly trigger the motor running forward and backwards to occur every time we were in the opening state, for instance, I'm just going to finish filling out this one. Okay, then what we would need to do is we would need to have a duplicate set of these states here. Just going to call this O2 and
It's going off the screen.
C2, thank you. So create a duplicate set of states, and for all of the behaviors where we wanted the system to remain in the current state, which I think was, for this top one, it was the bumper switch. Actually, this one was... Oh my gosh, bumper. Okay, so for opening it was bumper switch and sensor closed.
Wasn't it for all of them it was bumper switch, sensor closed and sensor open?
No, because if the door was opening, we said that if we get the bumper switch or the sensor is
opening.
closed, yeah,
Yep.
yeah, exactly. So bumper switch. And sensor closed. Takes us there, and then we can safely loop here. And I know this is going off the page at this point. Switch. Closed. Okay, so we have the bumper switch on the sensor. That allows us to remain in this state, but then we have to also handle all outgoing transitions from this state and duplicate them over to here. So we're going to add remote button, and we're also going to need to add sensor open, which I'm just going to run around the bottom here. Yeah, so we have to duplicate all of the outbound transitions from this one to this one so that they both behave the same when you receive those various other inputs. We have the same thing for this one. It's just sensor open for this one. And can loop on itself. Okay, and then again we have to duplicate all of the outbound transitions here. So, and again, I should have just shortened these even more. So remote button and bumper switch, and we also have sensor closed.
Wouldn't it be easier to do like you were doing in the previous example where you go from open to that open to dummy state? This just seems more convoluted.
Like, so which previous example?
The one where you crossed out, yeah, that one.
Yeah, I mean that's what we're doing here though. So because we've created this extra state here, we have to also match all of these transitions here. So every time you have a transition here, when you create the dummy state, you have to also match it for every outbound transition that you would otherwise have, which is what we're doing. So we have the closing state, we've created the dummy state C2 here for handling all of the sensor opens where we want nothing to happen as a result of that sensor being triggered. But then we also have to match all the outbound transitions. So we have an outbound transition from closing to opening, which we have to match. We have an outbound transition from closing to closed, which we have to match. And actually it was just those two. So that's that.
You're doing dummy states for closing and opening. You're not doing dummy states for closed and open?
In this particular case, yes.
Okay.
For the sake of the example, we are arguing that we don't want to repeatedly trigger the run motor, but we don't mind if we repeatedly trigger the stop motor behavior. But anytime that we have behavior that we explicitly do not want to have re-triggered, we need to create this set of dummy states in a more machine.
Right, I got backwards. I thought we had one of repeatedly triggered the stop motor, but we didn't care about the others.
Oh, good. Okay. So at this point, you might be like, well, that seems a bit ridiculous. Surely there's a better way. And it merely seemed really good. But then also I liked the fact that we had the reusability of the more machines. So someone decided that they could just combine the two and that we could arbitrarily apply the behaviors on the states and the behaviors on the transitions. So in terms of what that's going to look like, we're still going to end up having our 4 states just as we did before. And we can say that we have our stop, which always occurs whenever we enter the closed state. That always gets re-triggered. In fact, we can fill this out exactly the same as we did for the more machine, because we have this extra thing which we'll come back to. So I'm just going to start by duplicating most of what we had for the Moore machine. And this is run back and thing run motor forward. There we go. And open. And this was going to be okay. So now I think the first thing that's worth noting is because we can have behavior associated with the transition, we just noped out of what to do about this initial one, whereas in the Mealy system we added the run motor forwards to symbolize closing the door. So I can add that back into the transition again because we can have best of both worlds. So run motor forward. So we can actually have the behavior on the transition. That's nice. But we also have this funky thing called a partial transition that we introduce, which is representing an event occurring and us not actually leaving the state. So it's an explicit extra behavioral thing where we say, okay, this is different from a regular transition. I acknowledge that an event has occurred. I have planned it into my system. However, I'm explicitly not leaving this state. I'm remaining in the state. Or if you like, I am leaving the state, but I'm not re-triggering the entry conditions to the state or the entry events to the state. So the way that we represent that is with a nice little box like this. And then we just add the various behaviors or the various triggers that we wanted to that. So and closed. And we had the same thing over here. Partial transition. This was and then we can just fill out the rest pretty much the same as how we had it before, which is nice. So bumper switch closed. And the same thing here. And then button. Okay, and that's our basic Mealy Moore representation of the system. So we have, instead of explicitly writing out behavior under each transition and repeating the same behavior in a bunch of places, we can keep the behavior attached to the actual states themselves where applicable, If there are particular places where a certain piece of behavior applies on some transitions but not all transitions, we can peel that behavior off and apply it to just the transitions and leave it out of the actual states themselves. We have partial transitions to represent remaining in a particular state rather than exiting and re-entering, thus triggering the entry actions again, or in this case not triggering the entry actions again, which is good to have, and that fixes our counter problem nicely. So if we were doing this with a Mealy Moore machine, then this would look like y.
Could we do the partial transitions for the closed and open states as well?
We could absolutely do the partial transitions for the closed and open states as well if we wanted to, yes. So in a Mealy Moore machine, that would look like this. We could do that for this example here. Okay, so the big question is why. I mean, it's not the big question. It is a question. The question is why. What is the purpose of all of this? Why do we do these diagrams? What are the actual practical implications of that? And the practical implications come down to how we actually program the systems, because there is a way to translate this directly into code. And the reason why we have this as a design pattern is so that we have some explicit structure for how we write our code so that it always comes out in an appropriate way. So let's see, here we go.
All of this is just a branch of software architecture, isn't it?
Sorry?
All of this is just a branch of software architecture, isn't it?
Effectively, yeah. I assume you're doing design patterns in software architecture.
I've been doing design patterns for 4 years, but I'm not doing the core software architecture.
Fair enough. Yeah. So in terms of how we implement this as actual code, and there's a really good breakdown of this in the notes. So again, hopefully you've all seen this in the notes. But as we hopefully should know, the basic structure that we're going for in all of these systems is that you have hang on, remind myself. Right. The basic structure that we go for is that the events represent triggers in the system. These will be things that effectively trigger a function. So it's a functional kind of approach to programming effectively. So I might have a function for, and there's just some pseudocode here, but I might have a function for the button. And in here, what I'm going to do then is I'm going to say, okay, which state am I in? And then I'm going to transition to another state based on that. So typically that's done with a switch statement. You can use an if-else statement. So what we would do is first of all, we have a variable called state or something. Now, whether you implement this as like an enum of some sort, whether you implement this as just like a number, whether I tend to find that using constants is a nice convenient way to do it as well. As enums and constants are both convenient ways of doing it. So what I might start by declaring is some constants, and I might say open is 0 and const closed equals 1 and const opening equals 2 and closing equals 3, something like this. So I've defined each of my states. Again, if you want to use an enum for this, go for it. and I've defined a variable called state that's going to keep track of my current system state. I'm going to have a function called init, usually, that represents what we do when the system initializes. Doesn't have to be called init, whatever you want it to be called.
So
And
this is just pseudocode to just
yeah, this is just pseudocode. I'm crossing between about 4 different languages here. Hopefully you'll get the basic picture. So we set our state to whatever we want the state to be. In this case, I'm going to set it to closed as the initial thing that we do. If there were any actions that I wanted to take as part of entering or as part of initializing the system, now would be potentially one of the times to take them, depending on what type of system you're implementing. So in a merely system, we are just going to set our state variable to be whatever state it is that we're interested in changing to. And then we are going to have a basic switch for every input that we have. So if this is a switch, and then depending on what state I'm in, so if the state is going to be open, then I'm going to do some stuff. Again, I think I'm writing like halfway between Python and JavaScript here at the moment, but basic pseudocode, closed, and so on and so forth. Sorry?
looks closer to Java.
Looks closer to Java. Fair enough. So we define what each of the states are, and in a merely machine we have so this function represents the button is pressed, and we would have a function for every single input into the system. Each of them is going to be structured similar to this, where we say what is the current state of the system, and then if the state is open, we're going to do some stuff. In this case, when the button is pressed, if we take a look at our merely machine, if we are in the open state and the button is pressed, then what we want to do is we want to run the motor forward and we want to move to the closing state. So forward, state equals closing, something like that. And that's going to be our basic structure for implementing this as a merely machine. Now, if we're implementing as a more machine, in addition to what we have there, we're also going to define another function, which is going to be called, crud, what did we call it in here? Did they give it a name? Oh. In the notes they call it the next function. I'm going to call it goTo for argument's sake, but call it something that makes sense. Or change to. So we define this additional function, and this function carries the actual behavior for every single state that we are changing to. So what we would do, I should use this for variable naming consistency. So switch. So then we go, okay, well, what is the new state variable set to? And if it was open, for instance, then here is where we would apply the behavior that is applied every time we enter the open state. So in our more machine, for instance, we would always stop the motor when we entered the open state. So we would And in a Moore machine, you wouldn't actually have anything in here. When I say you wouldn't have anything in here, all that you would have in there for every, for every input that is received, instead of having the actions that you were taking and manually setting the state, you would always call this function that we have change to, and then whatever you wanted the state to be. I think we said it was open with the button, we were going to change to closing. And so we would do that, and after the switch statement was done, we would say state equals new state, like so. That's after the switch statement. So, yep, that looks like a look of confusion maybe. This is just a Moore, this is if we were doing strictly a Moore machine here. So we have this change to function that controls all the actual behavior.
So what about the trigger function?
Sorry?
Trigger function. Do we need to create a trigger function in here?
Checker fun?
Trigger the sensor.
No, so for example, the button function here, that is an event being triggered. So I mean, if we wanted to add that in, let's say we would have another function. I don't know, what would we call this? This was sensor open. And we would spell it correctly because that would help. And then we would have the same structure for that. So every input into the system is a function, and the thing that actually triggers these, the thing that is actually triggering these events to occur, that is an external input to our system. The way that our system interacts with the external world is that someone like starts our system, and then they start, pressing buttons or triggering sensors, and that is what is actually causing these functions to run. And each function running then in a Moore system is going to trigger this change to function, and the change to function is going to run actions and move us to the next state. And in a Milli-Moore machine, you have a hybrid of halfway in between. So you would, in addition to, you would keep the change to function, but then the structure is just that you could also add additional behavior in here. Let's stop motor, for instance. I know that we're already doing it there, but you could have additional behavior in there. And that's like the basic structure of code based on a Milli or a Moore or a Milli-Moore machine. And yeah.
Another question, because you already have the stop or motor function in the button.
Yeah, I should have chosen
Why
a
you
different. I should have chosen different behavior. I don't know. Something else that we could do. Our system doesn't do anything else. I don't know. We could do, I don't know, print. Hello. The point being that you could add additional behavior. In a Milli-Moore machine, you add additional behavior in addition to having this change to function here. In a Moore machine, you strictly apply all behavior in the change to function. Whereas in a Milli machine, you don't have the change to function at all. You set the variables directly, or you change the state directly in each of these input functions, and you don't have this change to function. And in a Milli-Moore machine, you combine them both together. So you have the change to function, but then you also have other behavior that you can run in line with these switch statements. The reason why a basic Moore machine can be created really eloquently using just like a matrix. If you had a matrix or like a multi-dimensional array that was basically just said, okay, this state with this, you can basically take a transition table, with a more machine, you take a transition table and you can basically plug it directly into code because the change to function can effectively act as a function that evaluates a transition table.
Yeah, more efficiency.
Yeah.
Just create a two-dimension array and then put all the status. Maybe top is input, and then
Yeah.
this is state, right?
Yeah, exactly. You could create a two-dimensional array, or if you were using like a language with like a map or an object that has like a hash map or something, then you could just evaluate the hash map based on the input, and you would get your output immediately, and that would be a very simple implementation of a Moore machine, and very eloquent and easy to do in code, which is why we even look at Moore machines in the first place.
So
As soon as you add this extra behavior in, you have to go through all of the extra steps with adding in switch statements and everything to.
So in the exam, if the question asks me to create a simple code, so could we just draw a 2D array and then write down all the status and input on it, and then just
If the exam asks you to do pseudocode for a Moore machine,
yeah.
you could do a 2D matrix approach to it, as long as your pseudocode appropriately addresses the 2D matrix as part of your change to functions. So I would be explicitly looking for an init function. We'd be looking for, again, a function for each of the inputs, but the difference is the input functions would trigger the change to function, and the change to function would then evaluate the matrix based on the input received.
The exam's gonna be in person, right?
Yes. Yeah. We're back to Wayville or something.
Not for me.
Not for you, but we're back.
Yeah.
For other people, we're back to Wayville. And for those of you learning remotely, we will have something going on, which we will know soon, hopefully. So less procedural and more functional? Absolutely. More functional, less procedural. I think that's the whole thing with event-driven computing. We're moving away from this procedural, in some cases procedural object-oriented approach to, it can stay object-oriented, but it's definitely a functional approach. Yeah. Okay. And that's that for today. Does anyone have any other questions they want to ask?
All the lectures are gonna be like this, where it's going through an example.
Yep. And that is because the notes are really solid, and also for the later sections, like, we're making sure that the books that we're referring to are all really solid as well, and that there'll be plenty of examples and other things. So that's the plan. Yeah.
I'm suffering in the assignment, so
Mhm.
can I ask you a few questions about the assignment?
Yeah, absolutely.
Yeah, actually, I try to start up my system first.
Fair enough. All right. For everyone else watching at home, if you have any other questions that you want to ask right now, feel free to ask them in the live discussion or in Piazza. And aside from that, again, a quick reminder of what's happening at the moment. Just come back to that. Programming assignment 1, get cracking on it. It's not a straightforward assignment. It is going to require a bit of... it's not a straightforward assignment. It's got a few layers to it. So make sure that you actually spend some time getting stuck into it to get a feel for what's going on. I'll be opening up the submission on Friday for that, and that will include some basic validation checks and other bits and pieces. But for the most part, that assignment's going to be marked manually. Again, workshops are odd weeks only, and the census date is Wednesday, so make sure if you are going to unenroll that you do so by Wednesday, if you are planning on doing so.
Is submission going to be through the school GitHub, so github.cs.adelaide?
No, you'll need to use a github.com account.
Oh, thank God.
Good question. Yes, no, we won't be using the school's GitHub server. You'll be using github.com because Gradescope doesn't support github.cs yet. So that's that.
That's what you using. Cool.
Yeah. All right, thanks everyone.